Okay, moving on to the next page. Remember, we're still under the same subsection here, so we are calculating mass. But in this case, we're starting with the quantity of atoms of uranium. So we've got 3.27 times 10 to the 13th atoms of uranium. Now, just like we have done in other cases, I want to put atoms of uranium on the bottom here. And now the question is, I want to get to grams in terms of mass. Grams and atoms don't really relate to each other, at least not directly. But I do know how many atoms are in a mole from Avogadro's number, or the Avogadro constant. So I know how many atoms are in a mole of uranium. 1 mole of uranium is 6.022 times 10 to the 23rd power atoms of uranium. And that's a big number, but again, it's kind of like dozen. If you had, 36 eggs, but you wanted to figure out how many dozen eggs that was, you could say, well, 1 dozen is 12 eggs. So we're just using a much larger number here, but we're really doing the same kind of scaling operation. Atoms of uranium would cancel out here. Now we have moles. Right? We've got moles of uranium. We know how to relate that to grams because grams to moles is one of the ways the mass we find in the periodic table can be described. So in the next step, I could put moles of uranium on the bottom, relate that to grams of uranium on top, and I would just need to find uranium on my periodic table. It's down here at the bottom. It's 238.03. So there are 238.03 grams of uranium in every mole of uranium. That would cancel out moles of uranium, give us the units we're looking for, which is grams of uranium. And now I just need to punch all this in. Now, there's a scientific notation on the bottom here, so this is a really good one to make sure you're punching things in correctly on your calculator, because if you're not, you may end up with a weird exponent at the end. So 3.27 times 10 to the 13th. I'm going to divide that by 6.022 times 10 to the 23rd. And then I'm going to multiply by 238.03. And what I get is, so 3 sig figs back here is my limit, 1.29 times 10 to the minus 8th grams of uranium. So it's a pretty tiny mass, right? This is just a fraction, not even, a tiny fraction of a mole of uranium. So much less than a gram here. Now, the one issue you may run into if you punch this in incorrectly, sometimes what your calculator will do is keep the 6 on the bottom of the fraction, but move the times 10 to the 23rd to the top of the fraction. And then you're basically multiplying by 10 to the 23rd when you should be dividing by 10 to the 23rd. And that'll move this by 46. So instead of minus 8, if you get plus 38 here, that might be an indication that you punched your scientific notation in incorrectly, and you might want to revisit how to do that using, right, I've got a Casio here, times 10 to the x is the best way to do it. On the TI-84, it's capital E, capital E. There's a key for that enters the multiplication sign without telling the calculator that you've put in another mathematical operation. Okay, moving on, a couple more examples here. For the next two, we want to calculate how many moles in the sample. So if we can go from grams to moles or atoms to moles to grams, we can do the opposite. So starting with the mass of chromium we have here in the first one, so grams of chromium. Right? Again, I want to cancel out grams, and since I'm trying to calculate moles, I want to change that to moles. Grams and moles, that relationship again is the periodic table. Right, so the trick here may be realizing when that's something you can find in the periodic table and when it's something you need to find somewhere else. Chromium's right here, it's 52.00. So 1 mole of chromium would be 52.00 grams of chromium. That cancels out grams. That gives me what I'm looking for, which is moles. So 50.74 divided by 52. And 4 significant figures here through my data, so I can keep forward my answer, 0.975 And then that last 7 is going to round up to 8 because I'm going to drop the 6 there. So 0.9758 moles of chromium in that sample. Okay, similar idea here, but we're starting with molecules, and we just want to get to moles. 3.65 times 10 to the 34th molecules of NH3 or ammonia. Right, and what I want to do here is cancel molecules. So I want to put molecules of NH3 on the bottom. I want to put moles of NH3 on top. That's what I'm trying to get to. And be careful with molecules. You can tend, if you're trying to abbreviate things, right? The reasonable way to abbreviate molecules would be MOL, but that's indistinguishable from how we're abbreviating moles. So my tendency is just to write out molecules when I write molecules, just so I don't get confused about what I'm actually trying to describe. Molecules in a mole, that's Avogadro's number. Now, people will get confused sometimes about atoms per mole versus molecules per mole. Up here in the uranium calculation, we used atoms of uranium per mole. Here we're using molecules per mole. The difference is what we're talking about. U, that's just an atom, right? Like we talked about back in chapter 1, but NH3, that's a molecule. So when we go to describe them in terms of how many moles, right, it does make a difference whether we're talking about molecules or atoms. So this is still Avogadro's number though. 1 mole is 6.022 times 10 to the 23rd power molecules. That would cancel out molecules, right? And this would tell us how many moles of ammonia would be in this sample. So 3.65 times 10 to the 34th power, right? And again, I'm dividing here, divided by 6.022 times 10 to the 23rd. And our answer should be 6.06 times 10 to the 10th power moles of NH3. Similar issue here, if you're punching in your scientific notation in a not ideal way, your calculator might break that into 2 pieces, and then you would end up with a much larger exponent in this case as well. So something to watch for. Okay, let's see if we can fit this last problem into this particular video. And it's following along, just it's more of a word problem style instead of just giving us what to start with. How many nitric acid molecules are in 4.20 grams of HNO3, which is nitric acid? So I have some data to start with here, 4.20 grams of HNO3. Right, now, whatever I do, I want to start with grams of HNO3 here. Now, from what we've talked about so far, we should probably be able to recognize, well, if I want to relate mass to something that's describing how many are present, I can get to moles. So moles of HNO3, well, that is the formula weight, or the molar mass. So if I add together the mass of a hydrogen, a nitrogen, and 3 oxygens, that'll give me the mass of the entire molecule. And we've seen hydrogen before, it's 1.01. Nitrogen is 14.01, right? Getting that from the periodic table. Oxygen is 16, so 3 times 16 would be 48. Right? And if I add those all together, 0.02, and I don't have them all lined up, which makes it a little harder. Say 8 plus 4 would be 12, 13, 3, carry the 1, 63.02, right? Maybe use your calculator there because I didn't leave enough space to really line them up the way that would be ideal. But 1 mole of HNO3 is 63.02 grams of HNO3. Now, once I get to moles, right, I can use Avogadro's number to get to molecules. So 1 mole of HNO3 is 6.022 times 10 to the 23rd molecules of HNO3. Right? And that would be the answer to the first part of that question. How many molecules are in this sample? So 4.2 divided by 63.02, and then times 6.022 times 10 to the 23rd, and 3 sig figs back here from my data, that would be 4.01 times 10 to the 22nd power molecules. Okay, now based on time, I think we'll stop right there. This is kind of a part B to that initial question, so we'll want to pick this up right at the beginning of the next video.